This meeting is being recorded.
Hello, can you hear me?
Yes.
Yes, we can.
Okay.
Do you alone need to have
When should I start? It's a bit early from the scheduled time, isn't it? Or should I just go ahead anyway?
Yes, we have 8 minutes for your talk. I want to show it first. Okay, Professor Robert. You can share your desktop now.
Should I share the screen now?
Yes.
Okay.
Perfect.
Let me get rid of that. Okay. So let me know when I should begin.
You can begin in 1 minute. Okay, I think you can start now. Thank you.
Okay, thank you, Mann, for organizing this meeting and for giving me the opportunity to present some recent work from my of my research and with my group on what I'm calling doubly holographic quantum black holes. So this work is basically, in some sense, can be understood as advancing this program of black hole chemistry that I've been doing for about 15 years now. And black hole chemistry basically is black hole thermodynamics, but with a different ingredient. So the idea is that uh, the mass, the surface gravity, and the horizon area of a black hole correspond to thermodynamic quantities. But in black hole chemistry, the mass is the enthalpy, um, surface gravity is temperature, and air horizon area corresponds to entropy here. And this, the reason why mass is enthalpy is because of this new ingredient. Well, maybe not so new now, it's 15 years old, uh, positing that in a space-time that has a cosmological constant, in particular a negative one, a black hole is in an environment with pressure, the pressure of the vacuum, basically. And so there is now a full correspondence between the first law of thermodynamics, where the change in enthalpy is the heat term, TDS, plus volume times the change in pressure, plus work terms. In standard black hole thermodynamics formulated 50 years ago, this term was absent, the VDP term. But once we include this, we see that in fact it should be there in black hole thermodynamics. And this was correspondence was developed in this paper by Castor, Ray, and Trashin. And to remind you of what enthalpy is, Enthalpy is the energy it takes to both make a system and place it in an environment. And the the way you can understand that here is that the mass of the black hole is the total energy of space-time minus the vacuum contribution. And E is infinite and rho V is infinite, but carefully calculated, their difference is finite, and it turns out to be the mass of the black hole, which can be understood as enthalpy. And we recall that when you have a cosmological constant, density is minus pressure, and so minus rho V becomes plus PV. Uh, although pressure as cosmological constant was formalized in this paper, there are hints that it happened. There were discussions of making the cosmological constant a thermodynamic variable that go back to the 1980s, and actually Jolyon Creighton and I formulated it in the 90s, but we didn't worry much about the conjugate variable of the volume, and black hole chemistry necessarily incorporates that. So there have been a lot of results over the years in the subject, and I don't have time to go through any of them in detail, but the early results are that the famous Hawking-Page transition, that a Schwarzschild anti-de Sitter black hole is thermodynamically unstable to dissolving into radiation at a cold enough temperature, can be understood as a solid liquid phase transition. So the large black hole is like the liquid, a higher entropy system, and the radiation is actually a lower entropy system. So it's more like a solid, counterintuitive though that may be. David Kubiznak and I showed that charged black holes could behave as van der Waals fluids, and they undergo small to large transitions, which are like undergoing a transition from a liquid to a gas. Again, the larger black hole is like the gas because it has higher entropy. And then we found that black holes can change from one phase to another and back again as one parameter, such as temperature or pressure, for example, monotonically changes. And we call those reentrant phase transitions. They were first discovered by a guy named Hudson in 1904, and I've got his little diagram here where he observed it in a water-nicotine mixture where water and nicotine are mixed at high temperatures, separate at colder temperatures, but mixed again at even colder temperatures. And then later on, as we pursued this subject, we found that black holes can have triple points, analogous to water, ice, and steam merging together at a particular pressure and temperature. And more recently, in the last few years in these papers, we found that black holes can exhibit multiple phases and multi-critical behavior where many phases can merge. Here's an example of multiple phases for a colloid, and it's been shown that certain colloids and polymers can have not just triple points, but quadruple points and quintuple points. And we show in these papers that black holes can have such points as well. It's been shown that black holes can behave like polymers, that the phase transitions from one black hole phase to another have non-standard critical exponents that are just like those of certain polymers. Black holes, when coupled to scalar hair, can exhibit phase transitions that are analogous to superfluid phase transitions in liquid helium. Clifford Johnson showed that black holes can behave like heat engines. And in this paper with Roby Hennegar, Fiona McCarthy, and Alvaro Balan, we showed that there is an theory-independent upper limit to the efficiency of a black hole understood as a heat engine. Accelerating black holes were discussed more recently, And counterintuitively, under certain circumstances, even though they're accelerating, they can behave like thermodynamic systems, and they exhibit new phenomena as well. There's a whole series of papers on this subject over here. Xiao Wenwei and Yui Xiaolu pointed out that black hole chemistry, if you take it seriously, suggests that the microstructure of black holes is not subatomic or even atomic, but rather it appears to be molecular. And we've shown that small charged anti-ADS black holes have both attractive interactions if the black hole is large enough, but if it's small enough, then the microstructure interactions seem to be repulsive. So these are a lot of results, quite a lot of papers written over the years. But the main point of this presentation now is holographic black hole chemistry, because this conference is about holography. So how do we understand a variable cosmological constant from a holographic perspective? And there have been a number, this was asked about 10 years ago, and there have been a number of results that have come out of this, asking this question. One is a holographic SMAR relation. Another is an understanding of holographic complexity in terms of thermodynamic volume. Another is that of central charge criticality, and then the quantum black holes. And I'm going to talk about these last two. I won't mention this work because there's only so much that I can put into any given talk. So what about variable cosmological constant and ADS-CFT? Well, the ADS-CFT correspondence formulated here by Maldacena in its original form, but now it's more broadly understood as gauge gravity duality. But in the original form, it was that gravity theory formulated on ADS5 cross S5 was dual to a non-gravitational SUN super Yang mills that had n equals 4 supersymmetry. And there have been thousands of papers written on this, as I'm sure the audience knows. But a key relation that emerges from this is this one right here that relates this n of SUN to the ADS length, which is related to lambda via the 10-dimensional Planck length. And so since L is related to lambda, it should be fixed because n is fixed. The n of SUN is some number, some integer. But variable pressure from black hole chemistry suggests lambda should be variable. So one way of understanding this is that n squared, or n, can be varied, and it has a conjugate chemical potential for the color, the SUN color of the super Yang-Mills theory. But another way, and the one that I think has been a bit more fruitful, is to understand this in terms of a variable volume of the field theory. That implicitly in here there is a volume of the space that the CFT is formulated on, and that can be varied. And Karch and Robinson pushed this viewpoint in this paper here. Now, I'm not going to discuss that, except to say that what they showed is that there was a duality relationship between the thermodynamic SMAR relation in the bulk and SMAR relation of the CFT on the boundary. And I'm going to mention how that was formulated more explicitly to give us an understanding of how the central charge plays the role of a critical parameter analogous to the way the pressure does in the bulk. And that was pointed out in this paper here with Juan Kong and David Kubiznak. So we start with the SMAR relation in the conformal field theory, which says the energy of the theory is the temperature times its entropy plus if there's charge in the CFT, the charge times its conjugate potential, and angular momentum times the conjugate angular velocity, and the central charge of the CFT times its conjugate variable mu, a chemical potential, if you like. Now, the central charge is related to n, and dimensional scaling suggests that it goes like L to the d minus 2, the ADS length to the number of dimensions minus 2, divided by Newton's constant times some variable k. That won't really matter here. Now, there's also a first law of thermodynamics in a conformal field theory, which looks like this right here. We vary the extents of variables a little bit and multiply by their conjugates. And when properly added up, you get the change in energy. Notice there is a pressure volume term that does not occur here because the PV term has no scaling properties in the CFT. Or rather, it's unitless scaling, I guess you could say. So what we did is take the holographic dictionary that says CFT energy should be like the mass of the black hole, noting that the charge and the electrostatic potential are related to the bulk quantities by terms of L divided by the square root of G. The others also follow straightforwardly for entropy and temperature and so on. I haven't written them down because these are the more interesting ones. But when you insert these relations in here, you get this kind of relationship where it looks like you need to vary Newton's constant. And when you do this, we discover that in order for this to be dual to that, this volume here, notice it's not the same as that script volume there. This volume here has to be related to these other quantities like so. And when we compute the conjugate potential for mu and c from the holographic dictionary using this relation, we end up getting the bulk-SMAR relation. This is a different way of doing what Karch and Robinson did. Now, varying Newton's constant seems to be a bit strange, and in fact, it's not necessary. And what we found a short while afterward in this paper here is that that the volume of the CFT is actually related to this conformal factor that relates the asymptotic ADS metric at some fixed radial value R to the line element ds squared of the CFT. So the CFT volume is like this, and we thought, well, why not vary omega? In other words, let's vary the size of the space of the volume of the CFT. So this gives us this extended holographic dictionary. This is why I didn't write down the other one on the previous slide. So the holographic dictionary says the CFT entropy is the bulk entropy, the mass and the black hole mass and CFT energy are related like so with this factor omega. Implicitly, people choose omega to be 1 by making the radius the ADS length, but that's not necessary. And when you lift that assumption that people generally make, you get this kind of dictionary here. And so now you can vary m over omega, and you discover you get this relationship here from the bulk first law. So in other words, assuming bulk first law the first law of thermodynamics in the bulk and rewriting things like so, we get this relationship right here. And when you use this holographic dictionary, this gives the boundary first law, which is just the same as the one I showed on the previous slide. So this is the demonstration, I've left out the technical steps, that the bulk first law is dual to the CFT boundary, provided you regard this CFT volume as being related to the conformal factor times the ADS length to this exponent here. So this allowed us to say we can now launch holographic black hole chemistry because we have a CFT first law that is exactly dual to the bulk first law. The variation of lambda is variation of not just the central charge, but of the central charge, the CFT volume, and the electric charge due to rescaling. It's not necessary to vary Newton's constant. And we can recover the equation of state and the SMAR relation. The SMAR relation I showed a couple of slides ago. The equation of state also necessarily comes out of these manipulations. So what I want to do now, so that is basically central charge criticality. What I want to do now is get to the quantum black holes, which is a new application of this holographic black hole chemistry. So I'm going to return to accelerating black holes. In fact, I'm going to go even farther back in history and write down the C metric, which is a very early solution to Einstein's theory of general relativity, discovered by Levi-Civita, and Weil also worked on it. And what was discovered is that this metric exactly solves the Einstein equations, where x, the coordinates are time, y, x, and phi. X you can think of as kind of like being the cosine of the polar angle, and y will turn out to be the inverse of the radial variable. Anyway, Levi-Civita found this solution over 100 years ago, and for a long time it sat around. Nobody knew quite what to do with it, how to interpret it, until Kinnersley and Walker came along. And they showed that little m can be understood as the mass, a can be understood as an acceleration parameter, E is a charge, if you have a charge. This actually is a solution to the Einstein-Maxwell equations. And K is a parameter. Don't confuse it with the K I had a few slides ago. K is a parameter that expresses the curvature of the x-phi space as either positive, spherical, zero, like a plane or a torus, or negative, like a hyperbola. And so Kinnersley and Walker showed that this metric, if you let y equal 1 over r and x go like cos theta, can be understood as a black hole accelerating rightward, being pulled by a line of stress energy that can be interpreted as a cosmic string. And so the black hole is stuck on the end of the cosmic string, which stretches out all the way to infinity and is basically pulling the black hole to infinity. And you can calculate the string tension from parameters here. Alpha is related to these other parameters. I haven't written it down. This is an exact boost symmetric black hole solution of Einstein's equations with an electromagnetic field and a cosmological constant, which is the lambda on the previous slide. And in fact, in general, this black hole will have an acceleration horizon. So it's accelerating along a hyperbolic trajectory here. So it has this acceleration horizon and it has a counterpart over here, and this is explicated in this paper here by Dias and Limas about 22 years ago now. So that's the short story of the black hole, and what I want to do is talk about the holography of quantum accelerating black holes. So here's the 3+1 dimensional accelerating black hole. And the basic idea is you take this thing and you slice this black hole with a brain. In other words, you insert a brain into the theory that cuts off this part of the space that is the cosmic string, but leaves the rest of this alone. So this gray area is the ADS bulk. This black part is a black hole with a horizon right here. And the blue thing is a brain that is placed at x equals 0. So the phi symmetry is a rotation about this axis. In other words, the azimuthal coordinate is going around this axis right here. And this brain here is a 2+1 dimensional world that has a 2+1 dimensional black hole on it. And it's called a quantum black hole for reasons that I will mention momentarily. And Roberto Emperan, Antonio Frasino, and Benson Way proposed this about 5 years ago now. And there is a charged version of it where you can take the charged accelerating black hole I showed you, and you could actually add rotation to it. I didn't show you that metric, but if you want to see it later, I can find it in other slides. So I looked at this version of the quantum black hole with this group of collaborators here from China, Feng Ma, Xue, and Zhang, and this appeared in JHEP last year. Concurrently with this work, Clement, Emperan, and Hennegar also looked at this, and we have some overlap here, but some different things as well. But the idea is the same. There is a black hole that is rotating about the phi axis, and it's charged. So it will have, when you slice it with a brain, it will have and in the bulk, it will have an outer horizon and an inner horizon. But likewise, on the brain, there is a 2+1 dimensional black hole that has an outer horizon and an inner horizon. And this brain slices the boundary of the ADS bulk, giving rise to what is called a defect conformal field theory, where the 2+1 dimensional brain intersects the ADS boundary. So we have three spaces. We have the bulk, we have the brain, and we have the boundary. So why do this? What is the reason for considering this so-called quantum black hole? Well, the quantum black hole is obtained like so. We have, as I pointed out a few slides ago, an asymptotically anti-de Sitter black hole, and that is accelerating, and it solves the classical Einstein field equations, Einstein-Maxwell equations, with a string source. But this can induce a codimension 1, the brain black hole, that solves semi-classical field equations. And this is what Emperan, Frasino, and Way pointed out. So if you like, the ADS black hole is the gravity, the ADS gravity from the ADS black hole is dual to a CFT on the ADS boundary. But by cutting it off with this brain, one is integrating out all the effects of the CFT that's cut off from that part of the boundary, and it affects the metric of the black hole on the brain. So the brain, if you like, is acting as, on the one hand, as an infrared cutoff in the bulk. It's not letting the entire space go to infinity, but it also is incorporating an ultraviolet cutoff from the CFT, because one is going to require that the black hole on the brain consistently solves a set of equations that are induced from the quantum corrections due to the CFT. And this construction has a number of interesting properties that are discussed in these various papers here. There's this paper by Frasino, Pedrazga, Sesko, and Visser that shows that variable lambda can be understood in from this perspective, that variations of the tension in the brain induce a variation of lambda in the bulk, which is an interesting and novel origin for black hole chemistry. It's been shown in these papers here that one can give stronger evidence for the weak cosmic censorship conjecture, and one also gains insights to the quantum Penrose inequality and to holographic thermodynamics. That's what I'll be spending some time talking about in this presentation. So let's go back to that Levi-Civita metric, the C metric, as it's called. Here it is again, so you don't have to remember what it is. And let's rewrite it by rescaling the cosmological constant, the acceleration. I'll rewrite K as negative kappa, and I'll rewrite MA as mu, and so on. And then we obtain this metric here. It's the same metric because I have just rescaled various parameters and coordinates. And here's y is 1 over r. So now we get something in this sector maybe a little more familiar. We get a Schwarzschild-like metric function, Schwarzschild ADS-like metric function, r squared over L squared plus this parameter kappa that's 1, 0, or -1, a mass type term, a charge type term. Here is the g of x. If you forget about these two terms, this is like 1 minus cos squared theta if kappa is 1, which would be sine squared, and this would be the usual spherical volume element. But we have omega here. L is 1 over the acceleration by this thing here, and I've written down what the gauge field potential is along with its field strength here. So this again is a solution to the Einstein equations, an exact solution with the cosmic string source. So and here it is. I just said it satisfies the Einstein-Maxwell equations with cosmological constant, where L4 squared is the ADS length squared, and it's related to the acceleration and another parameter, L3, that will play a role in this brain world construction. But at the moment, you can just say this metric solves these equations. Now, we have to worry about the parameter ranges of x. X actually goes from 0 to some finite value x1, where g vanishes. And we have to ensure that where g vanishes, we don't obtain a conical singularity. And what that has the effect of is it limits the magnitude of the charge on the black hole in terms of what x1 is. Or if there is no charge, x1 can go up to 1 when you have the spherical case. If you don't have the spherical case, then x1 can go from 0 to infinity. But if this is a spherical line element, then you have these restrictions. All right, so let's get back to this quantum black hole. And here I'm going to write it down for the charged and rotating case. What is done is you take this ADS black hole, slice it with a brain, and then make a copy of it, and then identify the brain here with the brain in this copy. So the entire space then becomes an ADS space once again, but the whole space is sliced with a brain, and in the middle of it is a black hole that is sliced by the brain, and so the brain itself has a black hole on it. So the brain metric is easily obtained. It's obtained by setting x to a fixed value of x equals 0. X increases around like so. And that function h that I mentioned is the same kind of Schwarzschild ADS-like thing, where the mass parameter is given in terms of minus kappa delta squared over 8g3, where delta has this value to ensure it's -2 over the first derivative of g evaluated at this value of x equals x1. And that ensures there's no conical singularities in the phi direction. So again, this one has to rescale phi. So this phi bar goes from 0 to 2 pi when I rescale it by delta, which means r needs to be rescaled by delta, hence the r bar. And so the other parameters just follow accordingly. So here is the brane metric with the gauge potential that I wrote. And the whole point of this is this brane metric doesn't satisfy the Einstein equations on the brane. Rather, it satisfies the semi-classical Einstein equations, where this T bar, this is just writing the G tensor in boldface and the stress energy tensor in boldface. It satisfies this. Sorry, this should be a G3 here. That's a typo. This is correct here, but this should be a G3. So this stress energy is induced by an effective action that is the action of the CFT on the boundary plus these other terms that are the cosmological constant term, the Ricci scalar also on the brane. So these are brane terms. But then these higher curvature corrections are induced from the quantum corrections due to the CFT. And there is also a nonlinear function that depends on the electromagnetic field strength and the curvature in 2+1 dimensions, the Riemann tensor in 2+1 on the brane. And these can be calculated in powers of this parameter L, which remember is 1 over the acceleration in the bulk. And they're rather lengthy and messy, but this is why it's called a quantum black hole. Maybe one should say it's a semi-classical quantum black hole, because the argument is by slicing off the brane, in slicing off the ADS space to put the black hole on the brane, and you have to require this metric to solve equations, and it will solve the equations that are induced by this CFT. So now let me, in the remaining time, get to this doubly holographic thermodynamics of this thing. So we have the bulk, where from black hole chemistry, the 4-dimensional pressure is related to the minus the 4-dimensional ADS lambda. Remember, lambda is negative for ADS, divided by the 4-dimensional G. And you can show that you get bulk equations, the bulk first law and a bulk SMAR formula, where this parameter here is related to the tension of the cosmic string and its conjugate variable here. And likewise in the SMAR formula, where we've got the pressure volume term. Now, these quantities are non-trivial to calculate, and I was going to put them on the slide, but I thought they're very messy. But this was already known from other work in accelerated black hole thermodynamics. But now we have the brane. And the idea here is we have a cosmological constant on the brane, and we have a central charge induced from the CFT way back here that's percolated down to the brane. And you can show that these variables in the bulk are related to the ones on the brain via the holographic dictionary. And this is a rather lengthy calculation. The messy work is in relating these variables to these ones here. So I'm just showing you the result that the 2 plus 1 first law and the 2 plus 1 SMAR formula are satisfied. I haven't shown you how. I'm sort of asking you to take my word for it, but we have shown that they are. You get a 0 here because the mass is unitless in 2 plus 1, unlike 3 plus 1. And so this becomes the SMAR relation. And then finally, we have the defect CFT on the boundary where the brain slices the bulk. And this CFT has a central charge and a volume related to the L3 constant of the brain, and there is a conjugate pressure. Rather, the volume is easy to calculate. The conjugate pressure from the energy induced onto this defect CFT in the boundary is not easy to calculate. But what we were able to do is show that the holographic dictionary from here to here also gives you a first law on the boundary and a SMAR relation on this boundary. So this is the doubly holographic thermodynamics. You've got a holographic black hole chemistry from here to here and from here to here. You've got it from bulk to brain and from brain to boundary. And if you want to see all the formulas for the mass, the charge, the pressure, and so on, this is it. This is for the non-rotating case. Now, we also, in this recent paper that's under review, took a look at the phase behavior. And here, in the interests of time, I think I've only got about 10 minutes left. I'll just sketch out some of the results that we have for these quantum black holes. Again, for the charged but non-rotating case, we find we get this rather interesting kind of phase diagram. If there is no charge, the neutral case, we get this inverted swallowtail structure. Now, the meaning of this is at high temperatures, the black hole will be in this state. But once you hit this temperature, it will be thermodynamically favorable for the free energy to drop and go into this state right here, which is a smaller black hole. And then it will evaporate up to here, and then it can't evaporate anymore along this branch, so it will jump up to the branch up here, which I cut off. But if if the black hole has charge below a certain value, then this curve doesn't go out forever, but rather there is an upper bound on the temperature of these quantum charged black holes. And so this curve is cut off, and you get a free energy diagram like this, where now you've got a rather complicated structure, and there is a phase transition here. There's another swallowtail crossover here where there is a phase transition. And so you've got a first order transition here and then a 0th order transition there. But if the charge as the charge gets bigger, this red dot moves more and more this way until eventually all you get is a cusp. And so in the overcharged case, above a certain upper bound for the charge, you find that there is a largest charge and there is an unstable branch and a stable branch. We looked at the critical exponents for these phase transitions, and surprisingly, we found that when the black hole was neutral, we got non-standard critical exponents. In fact, these are exactly the same exponents that I found a long time ago, about 10 years ago now, in this paper with Brian Dolan and Anna Kostuki and David Kubiznak, where the critical exponents are alpha 0, beta 1, gamma 2, and delta 3. These critical exponents govern the behavior of a system at criticality, and they're exponents of how things like the specific heat at constant pressure, or the change in volume near the critical point depend on the temperature. So this is specific heat will go like T minus T critical to the zero, for example, when alpha is zero. Now, once you add charge and or rotation, you find you get these exponents, which are the critical exponents that most black holes have. And beta is a half instead of 1, and gamma is 1 instead of 2. Alpha and delta are the same. You can show that despite this strange thing, different from mean field theory, that both the Rushbrook inequality and the Widom relation, which are standard relations of critical exponents in condensed matter theory, are obeyed for both the neutral case, the polymeric neutral case, and the mean field charged rotating case. I mentioned earlier the quantum Penrose inequality, so I will say a little bit about that here. So Roger Penrose showed quite a while ago that it appears that the ADM mass of a black hole is lower bounded by the square root of the area over 16 pi. And this is easily shown to be true for a Schwarzschild black hole, and it appears to be a general relation for black holes in Einstein gravity. Now, Frasino, Hennigar, Pedraza, and Sesko showed in this paper that these quantum black holes obey a generalization of this inequality, where instead of the mass, the ADM mass, you have to take the mass of the black hole minus the Casimir energy, which there is in this 2 + 1 case. They call it M Casimir, but this is really the Casimir energy. And this quantity here, multiplied by 8 times Newton's constant in 3 dimensions, is greater than or equal to this generalized entropy squared, as it turns out, divided by L3 squared times G3. The generalized entropy occurs because there are nonlinear terms in the curvature that are induced by the CFT quantum corrections, and so the entropy is no longer given by the circumference of the horizon. What we found in this paper here with my PhD student, Juman Bhattacharya, Roby Hennigar, and Ming Zhang, a visiting scholar from Jilin University, is that it appears that when you have charge and rotation, well, you get this additional term. Well, if you have zero rotation, then you reduce to this. But we discovered that the Penrose inequality seems to generalize to this inequality right here. So there's more to be understood as to why this is true, but this is what we found to be the case. Here I've written down, maybe I should have put these things here. The Casimir energy or Casimir mass is -1/8G3, and the generalized entropy is given by this quantity here. It is not simply the circumference of the horizon, but rather is this more complicated function of the horizon radius, this parameter x1, the rotation parameter a of the black hole, and so on. So one last thing, we studied the gyromagnetic ratio of these black holes. The gyromagnetic ratio is the ratio of the magnetic moment to the spin component. Basically, mu is G times S. For a Dirac electron, G is 2, and without quantum corrections. For a Kerr black hole, G is also 2. But for these quantum black holes, they actually are a function of the back reaction. And so if I write the phi component in terms of this parameter mu m, which is the magnetic moment, mu m is gm multiplied by this quantity right here that depends on parameters of the black hole. So for a Kerr black hole, this quantity is, oops, well, I didn't write it down. The Kerr limit is right here when there is no back reaction. And then the induced black hole has the same magnetic moment as the Kerr black hole. But as the back reaction parameter grows, I haven't written down what that is. It's a complicated function of the other parameters, but it basically grows and then asymptotes to a particular value here for this choice of parameters. This curve will move up and down maybe as you change this, but the qualitative structure is the same. So this is a rather interesting phenomenon, I think, where the gyromagnetic ratio of these quantum black holes depends on the CFT back reaction. Well, I'm going to close off here. I'm almost out of time. So there are a number of open questions about the holographic black hole chemistry in these doubly holographic black holes. What are the duals of all the bulk phenomena, triple point, superfluids, reentrant phase transitions? How do we incorporate higher order corrections in the CFT, the 1 over n corrections? What is holography telling us about black hole microstructure? Can we generalize this to other asymptotics? In fact, Juan Kong, Manus Visser, David Kubiznak, and I have recently done this for Lifshitz black holes in this paper here that actually I should change it. It just appeared as a Phys Rev D letter. So black holes do seem to behave like chemical systems, and there is a holographic understanding of them emerging. And there are certainly a lot of new things to do with this, but it's 5:19, so I will stop here and leave you with the thought that there's still a lot to learn from black hole chemistry, but I'll close with this assessment. I think there's enough information about the subject now to say that black hole thermodynamics really is black hole chemistry. And any theory of quantum gravity either better be rich enough to include and describe these phenomena in some effective way or emergent way, or if the phenomena are not there, there better be a really good reason why not. And I think holographic black hole chemistry, I hope, is going to provide us with new clues. So I'll stop here and thank you for your online attention.
Thank you. Is there any question? Let me ask a question, Professor. According to your doubly holographic thermodynamic description, does it suggest that quantum black hole act as a bridge between different effective description of holography?
Well, yes, I'm inclined to agree, and I don't think that's been as well studied as it might be, but I would guess the answer is yes. I think it probably does. Here, I can stop sharing, I guess, unless somebody wants to see a slide. So yeah, I think it does. Certainly, as I say, maybe I should have presented some of the equations, but the hard work in showing the bulk brane boundary thermodynamic duality is in properly identifying the parameters in one to the other. And that is a non-trivial job, but it does work. And I suppose you would say in hindsight, well, if it didn't work, what would that mean for holography? But now we know it does.
Thank you. Other questions? Okay, thank you very much for your
Okay,
advice.
thank you.
Thank you.
Let us to invite Professor Izzet Sakali, or invited speaker. And
Hello, Professor.
hello, how are you?
I am okay. Thank you very much, Professor Behnam.
I think, let me to